This is section 2.4, forces of friction. In this section, you're going to learn about friction and application of force of friction. You're going to have opportunity to review Newton's law and include friction on solving problems. The concept of the friction has its basis in surfaces that are not completely smooth. If you see it at that diagram under microscope, no matter how smooth the surface is, if you see it under microscope, you're going to see a lot of imperfection. So that surface doesn't look as smooth as you might have been expected. Imperfection of the surface will impact the friction. So the bigger the imperfection, the bigger the friction. But does the friction depend on a surface area, the surface in contact between object and the surface that is holding it? You can take a look of this example. There's a same box, same surface area that is holding that box. Now, if you place that box in a smaller surface area in a contact, based on a pressure, which is force that is applying toward that surface, divided by surface area, but that force is a force of gravity. So the weight of that block is going to push itself toward that surface area. So the pressure is going to make those two surface area in contact very close together. On another side, we have a block that is sitting on a wider surface area. It's the same block, same force of gravity, but this time, since the force is pushing on a bigger surface area in a wider surface area, then the pressure is smooth, is spread around, so that will make that surface area to be not as close as together as in the previous example. So that means that friction on a second one is smaller. However, this pressure and friction works together so that no matter how much is the surface area, even the small surface area will give you the same friction as a bigger surface area. So the answer would be no. Friction does not depend on a surface area because they cancel each other with the pressure. So what about rubber? Rubber is the only exception for any other material. So that's why we use rubber for car tires. So the bigger the surface area, the bigger the friction. So that's what we want. We want a bigger traction, bigger friction between tires and roads. So as a conclusion, no. Friction does not depend on surface area. When we talk about forces, we talk about force of friction as well, and we mentioned that there are two forces of friction, static force of friction and kinetic force of friction. We have rolling force of friction and we have air resistance that is a special case of a kinetic friction, but those are two major ones, and we're going to talk about those two one at a time. Static force of friction is a force exerted on a stationary object by a surface that prevent object from starting to move. So that means it's not moving. That's why we call stationary object. So that means if you see the couch here, if you push the couch, then it is going to be a static force of friction on another side that prevent the couch from moving, especially when the couch is on a carpet. That's a lot of friction there. Now on this box here, there is a surface, static force of friction that is generated between that surface. It is preventing that motion. So if you see that velocity is 0, that means that object is at rest. So what does it mean? No matter how much you push it, if the velocity is 0, that means that another force is generated by that surface in contact, and that is force of static friction. And here is a free body diagram that you do. So force of gravity, normal force, and you're going to see that normal force is responsible for force of friction, and then applied force, which is canceled by static force of friction. So applied force and static force of friction are canceling each other, and Fg and Fn are both canceling each other, same magnitude, opposite direction. So how can we calculate force of static friction? The formula is Fs for static force of friction is equal to mu s. Mu is a Greek letter you might have known by now. Mu s Fn. Remember, I want to draw your attention to the formula itself because many people make that mistake. It is mu s times Fn, not Fg. Yes, if the surface is horizontal and there is no other force acting on it, just two forces, force of gravity and normal force, and the object is not moving up or down, that is clearly very clear that you can use Fn is equal to Fg, then you can use Fg equals to mg in a formula. But formula itself is Fn, and I want you to always write Fs is equal to mu s Fn, not any other force, not Fg. Let's analyze the relationship between applied force and static force of friction. For this, we can use that diagram on the right when we can have a stationary object, and we can use a spring scale or a force sensor to pull it, a stationary object, along the horizontal surface. And obviously, there is a static force of friction acting on those on that surface between object and surface itself. At first, the sensor exerts no force at all. So the only two forces acting on that object on the diagram on the top, there is no force acting on the stationary object. As we pull gradually, more force will show. However, the object is still not moving due to a static force of friction. So the applied force and static force of friction will cancel each other. As we increase the applied force, if you see that on this diagram, the force is increasing, so will be a static force of friction until it reaches that what we call the maximum static force of friction. And beyond that point, if we increase the applied force, the object will start moving. So as a matter of fact, in the formula that we used before, you see that in that formula that we labeled as a Fs, as we usually do. As a matter of fact, it is a Fs maximum that we calculate in our problems when we solve a problem. We calculate the maximum static force of friction with mu s times Fn. Now let's talk about kinetic force of friction and difference between a static and kinetic force of friction. In the previous experiment, eventually when we apply force and that force becomes large enough to overcome static force of friction, the object will start moving. As the object will start moving, then there is no static force of friction acting on that object anymore because there is no stationary, it's moving. So kinetic force of friction will act on that object. So what is kinetic force of friction? Is the force exerted on a moving object by a surface that act in opposite direction of the motion. Remember, static force of friction was against attempted motion. Kinetic friction is moving. So kinetic friction is against motion of the object, direction of the motion of the object. Now, free body diagram is going to be applied force, but force of kinetic friction now, which if you see, is a slightly smaller. So you need a smaller applied force to keep the object moving compared to starting to move the object. Now, so in order to keep that object moving at a constant velocity, that means that F net has to be 0. So force applied is equal to a kinetic force of friction. How to calculate that kinetic force of friction? Similar, that the formula that we use for static force of friction. Only this time we use coefficient of kinetic friction. So coefficient of kinetic friction is the coefficient between two surfaces that are coefficient of friction between two surfaces that are moving. It is smaller, obviously, than static force of friction because kinetic friction is smaller than maximum static force of friction. Before we talk about coefficient of friction, we take a look of what we know about friction. There are three types of friction. Static friction and kinetic friction we already learned, and we're going to use those to solve the problems. However, just to mention, that is another type of friction that is a rolling friction, which is not covered in the lesson, and it is very small friction. So coefficient of rolling friction is smaller than coefficient of kinetic friction, and that is smaller than coefficient of static friction. That makes force of friction on a rolling motion, rolling friction, is less than kinetic force of friction, and that one actually is less than maximum static force of friction. So here are some values of coefficient of friction. If you take a look, the static force of friction and kinetic force of friction are closer together, but rolling is much, much, much smaller. So that's why, if you might have heard that the biggest invention is inventing the wheel. So that's why people sometimes saying that you don't have to reinvent the wheel. So that means that you don't have to do what somebody else have done already. Why? Because the invention of the wheel is by far the biggest invention in the automotive industry, in the moving stuff. It is very efficient because friction is tiny, very small friction. I think those lessons are most useful when it comes to a practice, when we solve a problem. For example, this is one of them. A cruise ship passenger uses a shuffleboard Q to push a shuffleboard disc of mass of 0.40 kilogram horizontally along the deck, so that the disc leaves a Q at a speed of 8.5 meters per second. The disc then slides at a distance of 8 meters. What is the coefficient of kinetic friction between disc and deck? So what is given? It's given a mass of the disc, 0.40 kilogram. Initial velocity is 8.5. Final velocity is not given, but it has to come to complete stop. Okay, so that means that final velocity is 0. And displacement, or a distance slide, is 8 meters. So what is asking there is find coefficient of kinetic friction. In order to do this, you can draw a free body diagram. So on an axis, you draw that object as a dot. Then the first thing you can draw is a force of gravity, and then a normal force, then force of kinetic friction, because on the right is the direction of the motion. So that would be a positive direction. Okay, so in a y-axis, there is no moving up or down. So that means that we apply a first Newton law on a y-axis and second Newton law on a x-axis. Let's start with the y. So f net y is equal fn plus fg is equal 0. So if you see that positive direction is up as normal, then normal force is positive and fg is negative. So we see that fn is equal to fg is equal to mg. Let's move to x-axis. So since that the fk is equal to mu k fn, so that means fk is equal mu k mg. So we can move to x-axis. X-axis is accelerated motion, second Newton law. So sum of all forces is equal m1a. F net x is equal sum of all forces. On x-axis we have only one force of kinetic friction, which is equal to m1a. So since the positive direction is on direction of the motion, Fk is negative. So minus Fk is equal to ma. So from here, since that we know that Fk, if you see above, Fk is equal mu k mg, now you have minus mu k mg is equal to ma. So masses will cancel, although it's given to us. So mu k is equal minus a over g. So a now you need to find out, because we have initial velocity, final velocity, and displacement. Using that one of those 5 kinematics formulas, you can find acceleration is 0 minus 8.5 meters per second, all this squared, divided by 2 times 8 meter, and answer will be minus 4.51 meter per second squared. And that is expected to be negative, because as you see from the free body diagram, the direction of the force of kinetic friction is always opposite of the motion. So it's a minus 4.51 meter per second squared. So now we are ready to find coefficient of kinetic friction, which is minus a divided by g, which is minus 4.51 meter per second squared divided by 9.8 meter per second squared. That is equal to 0.46. Here is another example. A 3 kilogram block of wood sits on a horizontal wooden floor. The largest horizontal force that can be applied to a block before it will start moving is 14.7 Newton. So what does it mean? Before it starts moving, that means it is maximum static force of friction. Calculate the coefficient of static friction for a block and a floor, so a surface between those two objects. What is given? Mass is 3 kilogram, applied force is 14.7 Newton, and mu s is equal to 0. Again, we can draw a free body diagram. Applied force and static force of friction. We have Fg and Fn canceling each other. So we can do the same way that we did before. On a y-axis, we do have equilibrium. Static equilibrium is not moving up and down. So that means F net is 0. So Fn is equal to Fg is equal to mg. So on an x-axis, we have two forces, Fa and Fs is equal to 0, because it's a static maximum before start moving. So that means it's a static equilibrium again. So Fa is equal minus Fs, then Fs is equal Fa is equal 14.7. Since that we know Fs, we know that Fs is equal mu s Fn. So from here we solve for mu s, which is Fs over Fn. But remember, Fn is equal to Fg and Fs is equal to Fa. So now we can say that Fs is replaced by Fa and Fn is replaced by Fg on those calculations. So we are ready to be able to calculate mu s, which is equal to 0.5. Now, once the blocks start moving, it takes only 8.8 Newton to keep it moving at constant velocity. So that means when the block is moving, now no longer static friction applies on it. It is a force of kinetic friction. So determine coefficient of kinetic friction. So again, we have a mass 3 kilogram, applied force is 8.8 Newton, and coefficient of kinetic friction is required. Again, we can draw a free body diagram. It's a similar one. The only difference is instead of Fs, so static force of friction, it is a Fk, kinetic force of friction. We do the same thing on a y-axis, is an equilibrium. So we can say that Fn is equal to Fg is equal to mg. So kinetic force of friction is mu k Fn, but Fn is equal to Fg is equal to mg. We can replace that Fn with mg. Then we can look at the x-axis. So it is a constant velocity. So that means it's a dynamic equilibrium. So F net is 0. So sum of forces are 2. Fa and Fk is equal to 0. We can actually label positive direction the direction of the motion. So Fk is negative and Fa is positive, but we're solving for Fk, so we can move the Fk from on another side of equation, becomes positive. So Fk is equal, Fa is equal 8.8. So from now, we are able actually to find coefficient of kinetic friction. So coefficient of kinetic friction is Fk over Fn. Remember, Fk is equal to Fa, 8.8 Newton, and Fn is equal to Fg is equal to mg. So mass is 3 kilogram and g is 9.8. When you do that calculation, you get Fk is equal to 0.299. So we have pretty much the same thing. So a 3 kilogram block of wood sits on a horizontal wooden floor. The largest horizontal force that can be applied to a block before it starts moving is 14.7. Calculate the maximum magnitude of static friction acting on a block if a 2.5 kilogram object is placed on top of it. Here is what is given. First of all, we had 3 kilogram block, and now we have another 2.5 kilogram, so it makes 5.5 kilogram. Coefficient of static friction we already calculated was 0.5. It's the same wooden block. It's not going to change. So what we're looking now is what is a new maximum static force of friction. So we draw a free body diagram as it was before, no change there. So Fn is equal to Fg, but now we have a total. So Fn total is equal to Fg total is equal to mass total times g, which is 5.5 kilogram times 9.8 is equal to 53.9 Newton. Now, we know from a formula that maximum static force of friction is equal to mu s Fn total. So 0.5 times 53.9 Newton is equal to 26.95 Newton. Friction is a complex concept. Friction sometimes is a problem. We address it. To minimize the negative effect of the friction in the moving parts, we use lubricant, for example, in a car engine. But sometimes friction is necessary. When a car is starting to move or a person starts to walk or run, friction is needed. We'll learn about this when we learn third Newton law as an action-reaction. So the ground is pushed backward and in return, ground push us forward. Ground push a tire forward, so the tires actually pushing the car, moving the car forward. Without friction, car cannot move, cannot slow down because it's going to be slippery, cannot turn the curves because it's going to slip off the road. So that's why it's very important for tires to be a good one, especially during the winter. That's why we use the winter tires. For us to walk, it is very important to have a good friction as well. Imagine when you walk on an icy floor, in a hockey floor, ice. It is very difficult because when we push ice backward, ice, because it's slippery, the friction is very small friction, doesn't push us forward. As a conclusion, we can say friction sometimes is desirable. A running shoe material and its shape, or material and shape that snow tires are made, are designed to have the highest coefficient of friction even when the ground is icy or wet. That's why the winter tires are designed differently and use different and softer material. Sometimes friction is not desirable. A hockey player shooting a puck toward the net does not want the puck to slow down, and the game will not be fun if that is played not in a smooth, icy surface. So as it moves across ice, the friction applies on the ice between ice and puck. It's going to eventually slow down, but what we are smoothing the surface on an ice ring to make it the friction as less as possible. So any moving parts, for example, in a engine or anything, we can use lubricant to minimize the friction as well. So sometimes friction is not desirable and we have to address it. We have to take care of stuff. Let's look at the physics of car brakes, ABS system practice. A car is traveling at 30 meters per second along the horizontal road. The coefficient of frictions are, coefficient of static friction is 0.50, coefficient of kinetic friction is 0.40. What is the braking distance, delta dA with ABS and delta dB without? So what is given? Coefficient of static friction 0.50, kinetic friction is 0.40. In V initial is 30 meters per second, V final is 0, has to come to complete stop. Delta dA and delta dB are required. Let's draw a free body diagram. Force of gravity and normal force, and let's label the positive direction are forward and up. On a y-axis, we have first Newton's law. F net is 0, so that means Fn plus Fg is equal to 0. Just follow the positive direction. Fn minus Fg is 0, so move the Fg to another side of the equation. Fn is equal to Fg. Now we can calculate the force of friction, which is a coefficient of friction times Fn, but Fn is equal to Fg, and Fg is equal to mg, so that means friction force is equal to mu F mg. On the x-axis, we have accelerated motion. So the only force is force of friction. So here we can follow the positive direction as well. Force of friction is negative, and we always label the acceleration as positive, but you'll see that it is going to come up as a negative value. So force of friction, we already calculated force of friction here, which is force of friction is equal mu F mg. So now minus force of friction is equal to ma. We replace the force of friction with mu F mg. So that means minus mu F mg is equal to ma. M and m cancel. So what is left? We can solve for a is equal mu f g. Now, with ABS, acceleration is static force of friction. As we mentioned, the whole role of ABS is to keep the wheel rolling, to keep the contact between tires and the road to be static. So static force of friction has to apply. So if you see that acceleration is equal minus 4.9 meter per second square, and without ABS is a kinetic friction because it's skidding, so is minus 3.92 meter per second. So where those numbers came from again is mu s is 0.5 times 9.8 is minus 4.9, and 0.4 times 9.8, it gives you 3.92, and with a minus in front, it's minus 3.92. Now, since that we do have acceleration, we can calculate displacement using that common formula from kinematics, V final minus V initial divided by 2A. So V final is 0, V initial is 30 meter per second, all squared, divided by 2 times minus 4.9 meter per second square. And answer here is 91.8. Let's do other one without ABS. So now with a kinetic friction instead of static friction. So the same thing is 0 minus 30 meter per second all in the square divided by 2 times minus 3.92 meter per second square. And the answer here is a 114.8 meter. If you see, there's a big difference on a braking distance. So when the car comes into complete stop, 91.8 with ABS and 114.8 without ABS. It's a huge difference. So it is much safer with ABS when we are braking. Interesting thing is the static force of friction is connected to motion. Static friction acts on an object when the object is at rest on a surface. Also, static force of friction can be used to make the object move. So actually we move because of the static force of friction. When we walk, the bottom of our shoe is at rest with respect of the ground and pushing backwards, so the ground will push us as a reaction forward. So now, what happened when we use those as we call a starting block? In a smaller race, especially 50 meter, 100 meter, and 200 meter, the start of the race is very important because since that race is short, you don't have really time to recover if you have a bad start. So that's why, to be fair with any athlete, we use starting block. So they are actually fixed on the ground, so we can push those starting athletes that run those races, push those blocks backward, and in return, based on third Newton law, those blocks is pushing that athlete forward, so it starts the race. So that's how the static force of friction, it is important because sometimes not only prevent the object from moving, but makes us to move, makes the object to move, makes the car to move. When an object is sliding across a surface, kinetic friction acts on that object in a direction opposite to the direction of the motion. Remember, kinetic friction is always against the motion. One common misconception is that kinetic friction always reduces the net force acting on object. That is not true. Sometimes you may see that both applied force and force of friction can act in the same direction. so it's producing the big net force. Sometimes they act on opposite direction, so the net force is sum of two forces. Since that they are in opposite direction, net force is going to be at a smaller magnitude. This is a practice problem involving friction. Two sleds are tied together with a rope. The coefficient of static friction between each sled and a snow is 0.22. A small child is sitting on a sled 1 with a total mass, so sled and a child, of 27 kilograms, and a larger child sits on a sled 2 with a total mass of 38 kilograms. An adult pulls on the sleds. What is the greatest horizontal force that an adult can exert on a sled 1 without moving either sled? So what we are looking at a diagram there is a force, horizontal force. So what is given? Total mass of both sleds and a child is 65 kilograms. Coefficient of static friction is 0.22 between a sled and a snow, and applied force is required. So what we need to do is draw a free body diagram of the total mass. So two sleds with two childs together, represented by that dot. Force of gravity, total force of gravity, and normal force are acting on that sled. And force, applied force, and force of friction as well. Okay, in order to find the applied force, we need actually to draw a free body diagram and apply a Newton's law on a y-axis and on an x-axis. Let's start with the y-axis. There are two forces acting on it. Total normal force and total force of gravity equals 0 because sleds are not moving up or down. So you follow positive direction, just keep it traditional. Up is positive. So Fn total is equal to Fg total is equal to M total G is equal to, plug the numbers, 637 Newton. We can do the same thing on an x-axis. We have two forces on x. The sled is not moving, so Fnet is 0. We can keep positive direction as a right, and Fa minus Fs is equal 0. So Fa is equal Fs, but we know that Fs, static force of friction, is mu s Fn, and we're talking about Fn total that we just calculated. 0.22 times 637 Newton is equal 140 Newton. B. Calculate the magnitude of tension in a rope between sled 1 and 2 when the adult exerts this greatest horizontal force. We already just calculated. So what is given is a mass 2 now. We're going to focus on sled 2 because the rope between two sleds is the one that is pulling only sled 2. So mass 2 is equal to 38 kilograms with a child. Static coefficient of friction is 0.22, and what we're looking for is a tension 2, tension between those two sleds. We, as always, draw a free body diagram. Fg2 in this case and Fn2, and then tension 2 is pulling on the right and friction is on the left. We keep those positive direction as a traditional up and right, and we do the same thing. We can calculate sum of forces on a y and sum of forces on x. Let's start with the y first. So sum of forces on a y is equal Fn2 plus Fg2 is equal 0. So we can follow positive direction. So Fn2 is positive, Fg2 is negative, it's equal 0. So Fn2 is equal to Fg2 is equal to m2g, and m2 is 38 kilogram and g is 9.8, and the answer is 372 Newton. We can do the same for F net x is equal to a sum of all forces is equal to 0. So we solve for T2 is equal to Fs2, static force of friction 2, is equal to a mu s Fn2. We just calculated Fn2. So 0.22 times 372 Newton is equal 81.9 Newton. Here is a practice problem number 2. It's very interesting example. If you want to conduct a lab, well, you want to find coefficient of static friction or kinetic friction. This is the way to do it, to approach. A book is resting on a tabletop with its front cover facing upward. You place a coin on the cover and slowly open a book until the coin starts to slide. The angle theta maximum is the angle of the cover just before the coin begins to slide. Find the coefficient of static friction, mu s, between the coin and the book. So, first of all, we have to draw a free body diagram, and this is very important because now we don't have a horizontal surface. We have surface with a certain angle theta. That's how we draw. We draw x-axis along the surface and a y-axis perpendicular to a surface. Then we draw force of gravity, which is always directed toward center of the earth, so downward. Then we split this into two components, x and y, because Fg is not on x, not on y, so we need to find its component. So then, after we know Fgy, we can draw Fn, because we know exactly that Fn and Fgy has to be the same magnitude. Then we draw static force of friction, and we draw that at a certain length because we know the only two forces on x are Fgx and Fs. So since that coin is not moving, we know that those magnitude of those two forces has to be the same. So that's how we do. We draw the free body diagram, and then we continue with applying Newton's law on both axes. Since that the object is not moving on both axes, we apply first Newton's law. So F net is equal 0. So F net is equal sum of all forces, which is equal 0. We pick the direction of the positive direction up and positive direction attempted motion, which is going to be following along the surface on the right. So Fn minus Fgy is equal 0. So we know Fn has to be equal to Fgy and has to be equal to mg cosine theta maximum. Why? Because it's adjacent of that angle. Now we do the same thing for x-axis. Sum of all forces is equal 0, and we have two forces. Positive direction is Fgx minus Fs is equal 0. So Fs is equal to Fgx, and since that Fgx is the opposite of the Fg, we use mg sine theta. Now, in order actually to calculate for coefficient of static friction, we know the formula is force of static friction divided by a normal force. But remember, static force of friction is equal to Fgx. We just found out on our x-axis. And Fn is equal to Fgy, the same way we did it when we talked about y-axis. Then we can replace fgx with what fgx is equal, so mg sine theta, and fgy is mg cosine theta. So mg and mg cancel, and what is left there? Sine over cosine is tan mu s is equal tan theta. So as a conclusion, coefficient of static friction depends on maximum angle. So in order to calculate that, we need to calculate tangent of the maximum angle before coin start to move. That is very important because tan is opposite over adjacent, and instead of measuring the angle, which actually is difficult, and the degree of accuracy is very low, then we can calculate or measure opposite and adjacent, and that's how we can actually conduct a lab, which is going to be very accurate, very accurate. Here's a practice problem with a static friction and motion. The coefficient of static friction between a person's shoe and the ground is 0.7. Determine the maximum magnitude of acceleration of the 62 kilogram person if he starts running on a horizontal surface from rest. So what is given? It's a mass 62 kilogram, coefficient of static friction is 0.7, acceleration is 0. Always we start with a free body diagram. Force of gravity and normal force, and then let's keep the moving on the right side, and static force of friction is on the left, and keep the positive up as a normal force, as a traditional one. Let's apply a first Newton law on a y-axis. So Fn plus Fg is equal 0, so Fnet is equal 0. We follow the positive direction, Fn is positive and Fg is negative. So Fn is equal to Fg is equal to mg is equal to 62 kilogram times 9.8 meter per second square is equal 607.6 Newton. Next one is x-axis. Sum of forces on x-axis is equal to ma. Now, just to a clarification here, the object is accelerating. We are accelerating. So starting from rest, we are moving. So that means we are changing the motion. So from rest to moving. So that's why sum of forces on x-axis has to be equal to ma. But the only force that is acting on x-axis is the static force of friction, actually, that push us forward. So static force of friction is negative, and acceleration is moving forward is positive. Static force of friction is equal to mu s Fn. That's formula. You can calculate it as a 0.7. Fn is equal to a 607.6 Newton. We already calculated. So static force of friction is 525.3 Newton. It is minus because that is a direction, opposite direction of the motion. Now acceleration is force divided by mass. So the force, sum of all forces, or net force, is equal to minus Fs. So if you take a look on the formula here, you see that minus Fs is equal to ma. If you solve for a here, is equal minus Fs divided by m. So that is minus 425.3 divided by 62 kilogram. That is plus 6.86 Newton per kilogram, or meter per second square. So that is exactly what we expect. We expect to be positive because acceleration is on that direction. So we push it backward, so the acceleration is going to be forward. Here's a practice problem that involves friction, static and kinetic friction. You pull a sled rope with a tension of 140 Newton, which makes an angle of 40 degrees with horizontal. The children's combined mass is 45 kg and the sled mass is 5 kg, 50 altogether. The sled is initially at rest. Coefficient of static friction is 0.20, coefficient of kinetic friction is 0.15. Find acceleration of the sled. So what is given? Mass total, 45 plus 5 makes 50 kg. Static coefficient of static friction is 20. Coefficient of kinetic friction is 0.15. Tension is 140 Newton. Angle is 40 degree. And acceleration is needed. As always, we draw a free body diagram. It's a gravitational total down and normal force total is up. Tension is with angle 40 degree, so we can resolve it into component, x and y. And then if you see that I draw the normal force, total normal force, shorter than force of gravity. Why? Because I know that tension has a y component, and together normal force and tension has to be equal with the force of gravity. So you do that as you practice more and get more confident with drawing a free body diagram. So on a y-axis, we don't have any motion up or down. So then the first Newton law is applied. F net is 0. So F net is equal to sum of all forces. We have 3 forces. We follow the positive direction, and then Fn total is positive. Y component of tension is positive, and Fg total is negative. We solve for Fn is equal to Fg total minus Ty. We actually solve those two components. Fg total is the mass time acceleration, which is 50 times 9.8 is equal to 490 Newton. Y component of that tension is opposite of that angle. That means that we use sine. So it's a 140 Newton times sine 40 is equal to 89.99. Then we round it to a 90.0 Newton. Then we solve for Fn is 490 minus 90 is 400. Then now, since that we know the formula of the static force of friction, which is mu s Fn, we can calculate static force of friction, which is 80 Newton. So we calculated static force of friction to make sure that static force of friction is smaller than x component of the tension. Otherwise, the sled will not even move at all, let alone to accelerate. So let's try to calculate it. So F net x is equal to Tx plus Fst, static force of friction. And we have to know that if that is bigger than 0 or 0. So we can follow the positive direction. So Tx is equal to T cosine theta, which is 40 degree, equals 140 Newton. Cosine 40 is equal 107.2. Then we can say Tx is positive and Fst is negative. So Tx is 107.2 Newton minus 80 Newton is equal to 27.2 Newton. So that means it's bigger than 0. That means that object will accelerate because we'll start moving, and the static force of friction will become a kinetic force of friction. So we do calculate now acceleration on x-axis, but remember, we have to calculate based on a new coefficient of kinetic friction, not static friction anymore. So after the x component of the tension will overcome static force of friction, then static force of friction will become a kinetic friction. So we can calculate what would be a kinetic friction. We know that the normal force is 400 Newton, and now kinetic force of friction would be 0.15 times 400 is 60 Newton. Then we do second Newton law on a x-axis. So that means that Tx plus Fk is equal to mta. We can follow the positive direction. So Tx is positive, Fk total, so kinetic force of friction total is negative. That is equal to mta. From here, we can calculate acceleration is Tx minus Fkt over mt. We can supply numbers. 107.2 minus 60, not 80, 60, because that is kinetic force of friction, divided by 50 kilogram, that's the total mass, is equal to 0.944 meter per second, or 0.94 meter per second. Here's another practice problem with friction. That is the same problem that we already did without friction when we talk about application of Newton's laws. However, now I included friction, so I use a red color so you can see the impact of the friction on solving the problem. So kinetic force of friction is 0.10 and everything else is the same as before. So mass 1 is 30 kilogram, mass 2 50, and applied force is 100 Newton. How to solve it? First, we label the masses, direction of the motion, and tension. So mass 1, mass 2, tension T1, direction of the acceleration is the direction of the motion, and positive direction. Same as before. So then we draw free body diagram of the object 1, force of gravity, normal force, we label it as G1, Fn1. Then tension on right side end, that was before, but now here is a difference. We have kinetic force of friction, and we label it Fk1 because it is acting on object 1. Okay. So next one would be choose the positive direction, and we can say F net, or sum of all forces, is equal to 0 on a y-axis. Why? Because the object is not moving up or down. So it's the first Newton law on a y-axis. So Fn1 plus Fg1 is equal to 0. So Fn1 is equal to Fg1, but Fg1 is equal to m1g, and now we can use it, because we need Fn1. Remember before, we didn't use the Fn1, but we can use now. So the answer will be 294 Newton. Why do we need Fn1, or normal force? Because we need to calculate Fk1, which is mu k Fn1. So 0.10 times 294 Newton is 29.4 Newton. Next one would be on an x-axis. Sum of all forces is equal to m1a, because we already know that is accelerating on an x-axis. So how many forces do we have on an x-axis? It's T1 and Fk1. So those are equal to m1a. So that means the acceleration is positive, and T1 is positive, and Fk1 is negative. So that will be equation number 1. We do the same thing for object number 2. Force of gravity, we label Fg2, Fn2. So force applied on the right, and there are two forces on the left. Tension 1, based on third Newton law, but we have another one, because we have friction, Fk2. And then we do pretty much the same thing. We label the positive direction, that's direction of the motion, And on a y-axis, it's easy because it's not moving. It's a first Newton law. So sum of all forces is equals 0. Although we follow the positive direction, that means Fn2 is equal to Fg2 is equal to m2g, and we can plug those numbers and we can find Fn2 490 Newton. Fk2, the same way as we did before, is equal to mu k Fn2, that is equal to 49 Newton. Okay, we're done with the y-axis. Now we can continue with x-axis. So sum of forces on x-axis is accelerating, by the way. And we have three forces. Applied force plus T1 plus Fk2 is equal to m2a. Remember, we have to follow positive direction. So Fa and acceleration are positive, T1 and Fk2 are negative. So we can write it. Fa minus T1 minus Fk2 is equal to m2a. That is equation number 2. Next step, as you already know, is just to add them together. Make sure the tension cancel, otherwise you have made some mistake. And then Fa minus Fk1 minus Fk2 is equal to m1a plus m2a. You factor a, with multiply m1 plus m2. You solve for a, and you see all in red are effect of kinetic force of friction. And we have now acceleration 0.27 Newton per kilogram. Now, next step would be calculate tension. You can use either of those two equations, but equation number 1 is shorter, easier. Then we can use that T1 is equal to M1A plus Fk1 equals 30 kilogram is M1 times 0.27 is A plus 29.4 Newton. That will give you 37.5 Newton. That is a tension. As you might have expected, I would go and redo the pulleys problem with a friction this time. So there is a friction between this object and a surface, and there's no friction here because it's in air, it's pending. That's the biggest mistake that people do. They forget that that's nothing to do with friction here. Air resistance is negligible. We're talking about friction only between two surfaces. And then let's go and solve it. As always, label masses and draw and label free body diagram. So direction of the tension, direction of the acceleration, positive direction. So object 1, Fg1, Fn1, it is pulled by tension 1 and then friction, Fk1. And we do the same thing on a y-axis. It's not moving up or down, so that means it's first Newton law on a y-axis. So sum of all forces is equal to 0, or F net is equal to 0, the same thing. So we have two forces, Fn1 and Fg1. Fn1 minus Fg1 is equal to 0. So Fn1 is equal to Fg1, but Fg1 is equal to m1g, and we can supply numbers there. It's 8 kilogram times 9.8. That is 78.4. And we can calculate coefficient of friction is 0.10 and 78.4. That will make force of friction 7.84 Newton. So we're done with y-axis. Now let's go at x-axis. Now on x-axis we do have acceleration. So F net is equal to m1a. Sum of all forces. How many forces do we have? We have 2. T1 and Fk1. We follow a positive direction. T1 is positive and Fk1 is negative. So that is equal to m1a, and that is equation number 1. If you see that very few changes because of the friction. We solve for object 2, free body diagram, Fg2 and T1. The direction of the motion is down because that object is falling down. So that will be a positive direction. And we have only y-axis. We don't have x-axis. So that's what we do. On a y-axis, we have acceleration. It's equal m2a. So we have two forces. Sum of all forces is equal Fg2 plus T1 is equal to m2a. Follow the positive direction, that is direction of the motion. That is not usual because we are used to put positive direction up. But since that is accelerating down, that will make our life easier to solve the problem. So the positive direction would be a direction of the motion and direction of the acceleration. So then Fg2 is positive minus T1 is equal to m2a. That is equation number 2. As you see, there is no friction here because that object, it is in air. There is no surface there. There is no normal force. Some people do that mistake. They draw in a free body diagram normal force. There's no normal force because there's no surface. Okay, so that's this step. So next step is to add those two equations together, make sure that tension cancel. And then on the left is left Fg2 minus Fk1. On the right, we have both M1A and M2A. So we factor A and we solve for A. Fg2 minus Fk1 divided by M1 plus M2. We plug those numbers and we get acceleration 6.05 Newton per kilogram or meter per second square. And the last step would be solve for T1. And we can use equation number 1. And then you plug those numbers there, 8 kilogram times 6.05, which is acceleration, we just calculated it, plus coefficient of friction that we calculated before is a 7.84 Newton. And answer would be 56.24. This is a last practice problem. Now this time we have 3 masses, 2 pulleys, 1 object that is on a surface that friction applies, the same coefficient of kinetic friction 0.10. Let's solve it, starting with the object, the labeling object, and labeling direction of the motion, which is a direction of the acceleration and positive direction. Start with the free body diagram with object 1, Fg1, Fn1, and then on the right is tension 1, on the left is tension 2, but remember we have kinetic friction for object 1, the only one that has friction. Then we can choose appropriate Newton's law. On a y-axis is first Newton law because it's not moving. On x-axis is second Newton law because it's accelerating. Sum of all forces on the y is equal to 0. Fn1 plus Fg1 is equal to 0. So Fn1 is positive, Fg1 is negative. We move that Fg1 on the other side of the equation, and then Fg1 is equal to m1g. So that is equal to 8 kilogram times 9.8. And that is equal to 78.4, and coefficient of friction is 7.84 Newton. Okay, and we go to x-axis when we do have acceleration. So sum of all forces equal to m1a. So sum of all forces is equal to T1 plus T2 plus Fk1 is equal to m1a. Now we can follow the positive direction. If you see, acceleration here is positive and T1 is positive. Those two are opposite, are negative. So let's do it. T1 minus T2 minus Fk1 is equal to m1a, and that will be equation number 1. Since that those two blocks are pending, are in air, there's no friction on both, we have exactly the same as we had before. So we start with the object 2, Fg2 and T1. So it is accelerating, direction is down, so that's why positive direction is down. But in regards of friction, there's no change because we already have done this. So sum of all forces is equal to m2a. And how many forces do we have? 2. Fg2 is positive and T1 is negative. So that will be equation number 2. So we have done it, and that's no effect of friction here at all. Same we can do for object number 3, draw a free body diagram, but this time, if you see, acceleration is up because this object is light, is pulled up by heavy one. So that means positive direction will be up. And then it's accelerating. We can use second Newton law, sum of all forces equal to M3A. And how many forces do we have? T2 and FG3. T2 is a positive, is up where the positive sign is. And FG3 is negative, so that's why we can write T1 minus FG3 is equal to M3A. That will be equation number 3. Next step is add those 3 equations together. And you see that T1 and T1 cancel, and T2 and T2 cancel because one is positive, one is negative. And then what is left is FG2 minus FK1 minus FG3. On our right side is M1A plus M2A plus M3A. So A is common, we factor it and solve for A. So what do we have here is FG2 is M2G and FG3 is M3G. You can factor G if you want, or you can do it slowly. Whatever you like, whatever is easier for you. So you plug those numbers in that formula and plug those numbers in your calculator, and you get acceleration is 2.35 Newton per kilogram. So remember that you need this acceleration because you need to calculate tensions. Okay, last step would be solving for T1. You can use equation number 2 because it includes T1. You solve for T1 is FG2 minus M2A. Solve for T1. Then FG2 is M2G minus M2A. That is equal to, so you can factor M2 because it's common, G minus A. That is 15 kilogram times 9.8 minus 2.35 Newton per kilogram. Kilogram and kilogram cancel. So what is left is 111.75 Newton. You do the same thing. Now you can choose equation number 3 because it includes T2. And you can solve for T2, which is FG3 plus M3A. FG3 is M3G plus M3A. That is equal to, you factor M3 times G plus A. Then you can plug those numbers there and you get 85.05. That's about for this lesson. I hope you learned something, and if you still need any help, please ask questions. Have a good one.